Welcome to an ultra-scale quick take video for PCI Express. In this video, we'll put together what would normally be a fairly complex system targeting PCI Express, DDR4, and some simple LEDs. We'll be using the power of IP Integrator, also known as IPI, to quickly build this system and make all of the needed connections. Once we have the system built, we'll download that design to a KCU105 board with a 20 nanometer Kintex ultrascale part. Finally, we'll use Jungo Connectivity's WinDriver software to look at the PCI Express configuration space, perform some simple reads and writes, and then have the option to generate software drivers for a number of different platforms. Let's go ahead and get started. So we've already got Vivado open. The first thing we want to do is create a new project. And let's go ahead and give our project a name. And once it has the name, go ahead and click Next, and Next until we get to the part selection. But here we want to select a board. And so let's look for the KCU105 board and go ahead and select it and then click Finish. So now we will get a project set up targeting that KCU105 board. And from here we'll go ahead and create a block diagram. And when our block diagram comes up, we want to make sure we have the board tab selected. And then within that board tab we can select DDR4 memory, which will put in a MIG block for us. We'll go ahead and select the LEDs so we have access to those. And we will select PCI Express. Now this is new in PCI Express. We want to select the link width. And so we'll select a by 4 link width. Now let's go ahead and open the PCI Express core, and so we can make some modifications to it. So we've already got by 4, but let's go ahead and also make it a Gen 2 design. We don't need to change anything with the IDs. And in the bars, we're going to select 3 bars, one for each of the 3 things we want to interface to. So the first one here, we'll go ahead and make a 64 kilobyte bar. And we're going to change the address translation to map it to AXI. So anything that hits this bar will now get if it hits the base of that bar, it'll get translated to address 400000. For memory, for the bar 1, we're going to change this to a 64 megabyte bar. This will be our DDR memory that we map into PCI Express space. Notice we give it a different offset. And then for our third bar, we'll also make it 64 kilobytes. Again, we won't use all of that, but we'll leave the translation address to 0. Let's go back real fast. We do not need to have a slave interface. The slave interface is where if we wanted to initiate reads and writes into PCI Express space, we're not going to do that here. So we can get rid of that so we don't have that. So let's go ahead and run the automation process and let that populate a lot of the different components that we would normally need to do by hand, and we can automate that process. Now the other thing that we do need to do is we need to add the clock buffer for PCI Express. So we'll select a utility buffer, and let's go ahead and drag it down here so it's a little bit closer where it's going to need to go. And here we can select from the board part that this is a PCI Express reference clock, and that will then automatically choose the iBuff DS GTE for us, and we can go ahead and connect that up appropriately to the sysclock GT and the MGT clock. And now let's go ahead and run the connection automation again, and that will connect up our PCI Express clock to the outside as well as our resets. Let's relay that out. So one of the things that we want to do is we want to change the interconnect. We want to add one more port because we're going to go to the PCI Express AXI Lite control port so we can look at the registers that are available in that piece of IP. So we'll make that connection. And then we need to connect up our clock and reset. So we need to put our clock back to the AXI control clock, as well as to the interconnect for both the clock and the reset. Now, one thing to notice is that we have this output clock from the MIG controlling a lot of the different interfaces, and this clock runs at 300 megahertz, and we don't need that 300 megahertz everywhere, especially if we're trying to close timing. Now, early in the process, in an earlier run, we had found that when we had that 300 megahertz reference clock, we couldn't close timing. So here you can see within the MIG GUI, we've got several output clocks we can select. One of the default ones is a 100 megahertz clock. Now I can make that even lower if I wanted to. We'll go ahead and leave it at 100 for now. So now what we're going to do is we're going to connect that 100 megahertz reference clock to the GPIO, as well as to the clock on the GPIO interface or interconnect. And then we're going to change that 100 megahertz because it's now the slowest clock. Going to the reset logic, we'll go ahead and connect it up that way. So we have our peripheral reset as we want it. We have our interconnect reset to the interconnect. We've got our PCI Express reset to the master interconnect. Now, one thing you see here, this master to slave interconnect for PCI Express, we don't necessarily need to have this reset come from this synchronizer. What we want to really do is have it come from the PCI Express reset itself. So we'll go ahead and delete that reset synchronizer, and we'll just bring that reset directly from the PCI Express block. Alright, so that is looking pretty good. Now we need to map our address registers, and we can just do this with automation, but what you'll see is they match with how we had things. So we have our DDR4 going to that offset of 8, we have our GPIO going to that offset of 4, and then we have our PCI Express control registers are right at base address 0 in the AXI space. Alright, let's go ahead and save that, and we'll go ahead and validate the design. Hopefully everything comes back okay. And it does. And so at this point we're done. We now have a hardware design that we're going to be able to use. So we'll go ahead and save this block design, and we'll go back into Vivado, and now what we need to do is we actually need to make the top level Verilog file. We're not going to make any changes to this Verilog file, so we'll let Vivado manage it. We'll go ahead and get it generated. And we can open it up here and take a look. We've got our PCI Express reference clocks. We've got the DDR interfaces. We should see the LEDs in here, but nothing that we need to change. Now there are a couple constraints that I want to add, and so we will go ahead and open up the constraints wizard here. We'll create a new constraints file. And once we have that, we will put in a clock period. So we do need to add that 100 megahertz reference clock period in there. We're also going to add some false paths just to make timing a little bit easier on the PCI Express reset pin. We're going to put a pull up on the PCI Express reset pin, and we'll also need to set the I/O standard so we can create a bit stream. And then going to the LEDs, we don't really care which 100 megahertz clock we get there on, so we'll add a false path going out to those LED pins. So pretty simple constraints. And now we can go ahead and run implementation, and we will speed this up so we don't have to sit through it. But we'll go through synthesis, we'll place and route the design, and when we get done we can go ahead and open up the design and take a look at it. So we'll go ahead and click on the Device tab, and that shows us a representation of the layout of how things have been placed and routed. If we go to the net list, we can actually select different parts of the design. So we'll select the interconnect and highlight it. We'll select the PCI Express bridge and highlight it, as well as the MIG DDR4 interface. And you can see each of these different parts of the design and how they were laid out. So let's go ahead and exit here, and we will go ahead and generate our bit stream. And we're going to take that bit stream and we will put it onto our KCU105 board that you see here. So our board is plugged in. Notice that it is a by 8 finger that's on there. We're only using 4 of the lanes. We could have used by 8. We'll go ahead and turn on the card, give it power. Now we're using external power here, so that allows us to program the card before we actually turn on the computer. So we go ahead and do auto connect. We see that our KU040 is recognized. We select program and we go ahead and program that design into it. When we do that, we should see the done pin go high, and then we can go ahead and turn on the PC. Alright, so once that PC boots here, we have WinDriver from Jungo Connectivity, and we'll go ahead and get it started. So here we see the Xilinx device has been found. We go ahead and click next, and that's going to let us look at the configuration space for PCI Express. So we see the device ID, the vendor ID, all of the things that we set already. Now, one of the nice things that WinDriver lets us do is it lets us do some simple writes and reads, for that matter, to the system. So if we write to the LED and we write a 1, we see that we do get that first bit of the LED turned on. If we write a 3, it's the first 2 bits. And then if we write FF, we can actually turn on all of those LED bits. And then we can go ahead and write zeros back to them, and that will turn them off. So this is a really nice application for if you need to control LEDs on the board from the host operating system. Now bar 1, if you'll recall, was our MIG interface to DDR4. So if we do a read, we see this pattern that looks like it's set to a certain value, and indeed it is. That is one of the test patterns. But we'll go ahead and write a new value to it. We'll go ahead and read back. We're going to change our offset to address 4. Just read back, make sure we're not getting the same value. Change it back to 0, and indeed we see the value that was written in there. Now if we go to bar 2, this is the memory space for PCI Express, and PG194 actually points us to PG156. This is the PCI Express configuration space, but it's being read through the AXI interface. Alright, so now let's take a look at how we would generate the driver for a different operating system. So here you can see there's a bunch of different options for us to select different source code. We're going to go ahead and choose just a Linux makefile and select OK. And we'll go ahead and save that into a project here called Xilinx MIG. I've already saved it once. We'll just go ahead and overwrite it, but you would generate that on your own, and we'll get a list of files. Alright, so once we have that done, we're going to go ahead and switch over to the Linux operating system. It's already run up and booted. We have our Xilinx PCI Express card installed in this Linux operating system. Now the first thing that we need to do on this side of, in this operating system, is we need to install the WinDriver and make sure that it is loaded up. So to do that, you install WinDriver, and you can go to the Jungo Systems website and get information how to install that. And once it's installed, you go into this redistribution directory, run the /configure, and then we're going to run make clean and then make install. And what that does is that will load that driver up into the memory space. Now we could put that into the power on scripts that run when the system boots. I don't have that, so we have to do that here. All right, so now let's switch over to the directory where I have copied over the files that we made on our Windows system. And you can see here we have a nice file list that tells us all of the different files that are in this directory. And if we go into the Linux directory, you'll find that there's a make file in there. And that make file is going to compile the, well, before we do that, we have to set a variable that tells us where WinDriver is installed. So we'll go ahead and do that. And then once we do that, we can go ahead and run the make file, which will create an executable. When we create that executable, you'll see that it finds our device, and there's a bunch of options that we can now run again. Reads and writes to memory space, reads and writes to configuration space. So there you go. In a little over 15 minutes, we've created a full PCI Express core, as well as drivers and example code for not one, but 2 operating systems. Well, that concludes our creating a PCI Express design in IPI. We hope you found it useful. If you have any other questions, please leave us comments, and we will try to answer them as quickly as we can. Thanks for your time.
Thanks for viewing this quick take. If you found this video useful, you might be interested in taking some of our more in-depth training available at xilinx.com/training. We feature a variety of courses, both live and online, intended to make you proficient with Vivado and its features. We look forward to your participation. Thanks again for making Vivado successful.